second part of the decision diagram tutorial. In the first part you've learned how we create relaxed decision diagrams and how they can be useful in optimization. And in this tutorial I'm going to talk about the application of sequencing and scheduling, particularly disjunctive scheduling or single machine scheduling. We do have material available on web. Here's the website. It contains presentations, papers, code, benchmarks and so forth. If there's something you would like and it's not there yet, for example the latest version of the scheduling code, send me an email and I'm happy to share that with you. I also think I'm going to plan for a sanitary break in about 45 minutes, depending on how things go. But let's get started. So, decision diagrams are well-known concepts, data structures from computer science, and there are a few new phases here, so I'm going to repeat a little bit of what Jan said in the very first 2-3 slides in his presentation. Repetition is not bad necessarily, I think, but in that previous tutorial you saw how decision diagrams can be useful to generate bounds on objective functions, for example, and how they can be competitive to state-of-the-art integer programming solvers for problems like stable set, maximum cuts, max2 set, or even inventory management problems. The main thing that's different from anything else you probably have seen with decision diagrams in the context of AI is that we are trying to create approximations, relaxed decision diagrams that give us bounds on the objective. So this relaxation concept is the main differentiator between the other works and what we are doing. And today, so what I'm going to do, I'm going to apply the things now to the context of sequencing and scheduling, so I'm going to present everything in that context. It turns out that my scheduling problems will be constraint-based scheduling problems. That's my methodology. It's a very generic methodology because it borrows everything from constraint programming, which in itself is as general as integer programming or the like. So what I will first do is introduce to you MDD-based constraint propagation and constraint programming with decision diagrams. It's not going to be very long, and it may be a good reminder of what constraint programming is and how generic it is. This is important because what we do is not going to be tailored specifically only to sequencing problems. If you have a more complex problem with more complex constraints, since we live in the larger framework of CP, you can just add anything you like, any side constraint to your problem. So it becomes very rich as an expressive system. Hopefully, if you have time, I can also discuss how we can handle state-dependent costs. I will discuss the time-dependent traveling salesman problem for that purpose, but it's again quite generic. But that's what I will talk about right now. But I will start with a brief introduction yet again about decision diagrams. If you have seen this in the previous tutorial, it's a good time to check your Facebook or Twitter. It's just taking probably 2 or 3 minutes. But let's just refresh our memory what decision diagrams are and how we will use them. So basically, they are used to represent Boolean functions, and I have here several ways of representing it, 4 different ways. So you can build or you can do it in an algebraic manner, like here it's a conjunctive normal form. It's a Boolean function returning either true or false based on the inputs for the Boolean variables here, x1 to x3. You can of course also represent it via a table or a decision tree right here. Maybe I can move this up a little bit. So in a decision tree, you take a variable and it takes either value false or true, and depending on that, you take the next variable and so forth, and the leaf nodes denote 0 or 1, true or false for your function. Now these decision trees and these tables become exponentially large if you list out all possible tuples of variable value assignments. And what you can do also is represent this tree more compactly using a decision diagram right here on the right that encodes all solutions, but in a more compact manner. How do you get them? There are different ways of doing it, and the most common way in the Boolean world is to merge isomorphic subtrees. So if you identify subtrees here that are the same, you can merge them and you can move on iteratively. That's a very cumbersome way, and also if you do this, you would have to first create an exponentially large tree and then do this merging. If you do it like that, which is not what you typically do, you can also build them up, for example, by representing these individual clauses exactly using small decision diagrams and then joining them basically, or taking the intersection. That's another way of doing it. Which is not the way that we will do it, but that's one way in literature that they have done it. It's a very old field. It's one of the most highly cited papers in computer science, at least when there was no machine learning papers yet on the market. The Bright, for example, is also at CMU, wrote a very influential paper. The So Boolean or binary decision diagrams have only 0 and 1 arcs going out of each state, and the decision diagram means I can only have, in this case, a deterministic choice. It's either 0 or 1, and you cannot have 2 0 arcs coming out of one state. You have just one possible label out of each state. That's the crucial thing here. But we can extend this to multi-value decision diagrams where you can have any set, any finite set taken out of a state. Okay? And each value can only occur once out of each state. I will work mainly with MDDs, multi-value decision diagrams, in this talk, and John will focus mostly on binary decision diagrams. So they were introduced in the context of circuit verification mainly, and verification in general. And most of the AI literature or CS literature focused on reduced ordered BDDs, meaning they have to be as small as possible, and there's a unique reduced order BDD for a given problem. And they try to achieve that reduced order time. You have a fixed variable ordering and just a minimum. This is, as I said before, decades of literature. In the optimization world, around the mid-2000s, people started recognizing these data structures as a tool, for example, for cut generation, for integer programming, or facet enumeration, and post-optimality analysis. So you have this decision diagram represents, for example, all solutions within 10% of your optimal objective value, and then you can maybe pull out other solutions that are to your liking. Or in constraint propagation, you can also use these tools. Now, all of these were exponential size, or in any case, well, if you're lucky, they're not, but they didn't have any restriction on the size a priori. So they all work with exponentially large, in general, decision diagrams, and of course, this limits their application. If you are familiar with SAT, Boolean satisfiability, they also used it in that context quite successfully up to the state where you have this exponential blow up, and then at some point you cannot use them anymore. So the typical barrier of application is this exponential size. If you have a specific application, maybe you can get around it. If you have not such specific application that limits your size a priori, then you're doomed and you may not want to use it. So luckily now we have relaxed decision diagrams introduced by John and others in CP2 in 2007, the conference, which creates forcefully polynomial size decision diagrams. So it makes sure that the decision diagram is of polynomial size, however it's no longer exact. That's fine, because we can use it still for inference, for bounding, and for search. So that's what we will focus on in this tutorial. And this is really what makes it work in practice. To show you how you can apply this in optimization, and some of you have seen this already, a large part of you have seen this already, what you could do is you could create a huge enumeration tree for a given combinatorial optimization problem. For example, here I have a set covering problem with 3 constraints and 5 variables. I have to satisfy all these 3 constraints. So what I could do, if I want to find all solutions to this set of constraints, I can enumerate all possible variable value assignments and build this search tree basically. And here I have a 1 if I satisfy all constraints and a 0 if I don't. If I were given this, I can now create my decision diagram by merging isomorphic subtrees. For example, I could merge these 2 little trees here, 0 and 0, because they're isomorphic, and now I have a smaller decision diagram. So I take decision tree and turn it into a decision diagram. If I'm interested only in feasible solutions, I might as well just get rid of all the zeros and focus only on the feasible set, and then merge isomorphic subtrees. For example, those 2 are the same. So they lead to the same solutions, so I could just merge them. And if you do that, then you can get your decision diagram like this. As I said before, this is a very impractical way of doing it, because you don't have the exponentially large search tree to begin with, but this is just conceptually what we are after. We would like to have this set, and if we have this, we have solved the problem. A path in this diagram gives you a solution, and every solution corresponds to a path. So there's a one-to-one correspondence. Okay. So in the rest I'm going to talk about the root here and the terminal there. These are just 2 concepts that I will use all the time. And the problem is their exponential size. And what we will do is we will try to make them more practical by limiting the width, as John mentioned also before. The width is the number of nodes on any layer, and then the maximum of that number. In this case, the width of this decision diagram is 4, because this layer has 4 nodes. If you cannot represent this MDD in your computer because this width is too large, you can arbitrarily limit the width to maybe 3 or 2, and then compress it more by giving up examples. Well, I think this one we can represent, but don't be fooled, because there may be exponentially many information buried here under the states. My states can be extremely large, perhaps, so even this small MDD may not fit in your computer. Well, I probably will, but it fits on mine because I can display it. Here you are. So that's what we'll do. And I'll show you in the context of decision of constraint programming how we can use them. So this was the brief summary of what John told you also in the previous tutorial. So everything that I'm going to talk about in sequencing and scheduling relies on constraint programming, constraint-based scheduling. So I'll give you a very brief introduction to constraint programming. You have seen this probably before, maybe in one of your AI courses. This is a one-slide introduction to CP. And the workhorse of constraint programming is, of course, search and constraint propagation. So if you just focus on a given problem like this, we have 3 different constraints here, and each variable has a finite domain, like this. And you want to find a solution that satisfies all 3 constraints. It's a very small problem. Maybe you already see the solution. This constraint, all different, means that they should all take different values, so they should all take distinct values. It's a permutation constraint. Okay. If you don't see the solution, that's fine. I'll show you one in a second. So how does a constraint programming solver solve this? Well, basically by smart enumeration, smart search. But it does domain reduction, filtering to make the search space as small as possible. And since these constraints can be combinatorial, like for example, all different is really a strong combinatorial structure that may even be hard to filter completely, we cannot group them all together and reason on them all together in one shot, as for example linear programming would do, or interprogramming would do with linear programming relaxation. We treat them all separately, and what we can deduce from the first constraint, if we treat that in isolation, we can deduce that 2 and 3 cannot be assigned to variable 2, because there is no solution that takes an element from x1 that would satisfy it. Okay? So we have reduced the domain of x2, and then we go to the next constraint, and we deduce more. Well, we cannot do it. Everything is fine, and then the all different. What we can identify is that 0, 1 and 0, 1 will be taken by x2 and x4 in some combination. So they cannot be taken elsewhere, so 1 can be removed from this one. And then we can remove 2 from here, because this is now fixed. And you can continue doing this and propagate the updated domains until you reach a fixed point. Here I have a fixed point, and it is a solution 2, 1, 3, 0. It satisfies all 3 constraints, it's all different, and now I'm done. This is a beautiful application because we have just used propagation to find a solution. Generally, of course, the domains do not need to be empty or of single value, so we have to search on them and then it gives you your solution. Great. This can work very well, but not always. What's the problem? It can be weak, and I'll show you one example here. I have an all different constraint, and this very simple sum here, and these finite domains 1 and 2, 4. There's something called domain consistency, meaning a constraint is domain consistent if I cannot reduce the domains any further. Both constraints are domain consistent. With these full domains 1, 2, 3, 4, there's nothing I can deduce for the all different constraint in isolation. And there's nothing I could do with respect to, I can take a 1 for x1 and take a 4 and a 4 here. Right? Because if I consider the second constraint, a 1, a 4, and a 4, of course it doesn't satisfy the all different constraint. But I don't know that because I'm treating this in isolation, and all different is treated in isolation. So I have a witness for 1, I have a witness for 4, and everything in between, so basically I cannot deduce anything. But there is much more information here, because I know when I do the test for feasibility for 1, 4, 4, I'm violating the all different constraints, right? So I should not be allowed to do that. So suppose I could list all solutions to the all different. They're right here, all permutations. Okay? Suppose my constraint propagation engine is allowed to go into the all different and into the list and now evaluate the second constraint. So if I do this first if I look at the list, of course, if I project all these tuples, I get the original domains back. If I look at the second constraint, and I will check which of these tuples satisfy the second constraint, I can eliminate that one, because it is value 10, this is 10, this is 10. So many of them can be removed from the list. Now normally I don't know this, because I don't know that the list of tuples are all different when I treat the second constraint, but if I could do it, this would be very strong. And if I could do that, I could actually get a list of tuples that is completely filtered with respect to the second constraint. So I basically take the intersection of the second and the first constraint. If I now project back on X4, I have only 1 in this place, and I can actually reduce the domain dramatically. Okay? Likewise, I can deduce that the other domain should be 2, 3, 4. So why is this so important? Well, I could not deduce this by only propagating domains. There is structural information in the old inference constraint, and also in the other one, that if you project it down on the variable domains, it's completely lost, the propagation structure. If I can somehow communicate that structure to the other constraints, I could be doing much more. So ideally what I want to do, of course, take the intersection of all constraints at the same time, which is then hard to do, or exponential to do. But I could perhaps do better. Instead of using all the solutions explicitly, I might use MDDs. And maybe MDDs in themselves already can represent this exponentially long list much more compactly. This is the exact representation of all these tuples. So what I'm now going to propose is move, or give, instead of the domains, instead of domain propagation, do MDD propagation. Represent your solutions for one constraint using an MDD, a decision diagram, and move the decision diagram from constraint to constraint. The diagram has the opportunity to exploit structural relationships among variables. Okay? If I do that, you can project this MDD now, and you see that this is 2, 3, 4 for the first 3 layers, and 1 for the first one. So if you project it down on the variable domain, you get exactly our inference. Okay? And that's the idea. And this is much more powerful if we are allowing and able to do the exact MDD and give the exact MDD from one constraint to the next, which makes it exact again, and so forth. We would solve our problem in one shot. And it's going to be NP hard, I know that, but that would be our goal. But we can't. But we want to represent better the relationships among variables than the Cartesian product of variable domains. And instead of having the exact MDD, which is this exponential thing, we're going to do the relaxed. We're going to use a relaxed MDD. So maybe not a width 3, but maybe width 2 MDD is already sufficient to do some inference that is much better than we used to have only with the domains. So we're going to give to the solver, the CP solver, an MDD representing a subset of variables, and an a priori width, and I say you can use whatever you want to represent the Cartesian product of the variable domains in a smarter way within that width, and then I propagate that MDD from one constraint to the next. So how does that work? Well, I just augment my CP solver that already has this constraint propagation mechanism with my MDDs. Maybe I start with a very simple one and I refine it as I go, but I will show you later how it works in detail. And instead of filtering the domains, I'm going to filter edges here. Maybe I can deduce that this edge is inconsistent or infeasible. Maybe this edge is infeasible. So I will propagate edge updates from my my constraint propagation mechanism now must filter edges in the MDD rather than just filter domain values. Okay. And I might also refine, split the nodes if there is more space to do that. And the search is exactly the same. So that's the idea of MDD-based constraint propagation. If you would do this, the task is quite big. Now you have to go over all constraints in your library. Some of these are listed here. And you have to augment those existing propagation algorithms, and you have to make them suitable for MDDs. They should receive a decision diagram, and instead of just doing the domain updates, now you have to update the MDD. We have done that for you and for many other people, so now you can look at that and see how that works. So let's, for example, look at one such constraint, the among constraint, which is in CP of all these weird names, but this particular constraint says that among a set of variables in X, take between L and U from a set S. For example, suppose you have a nurse scheduling problem, and the variables represent the shift I'm going to do on each day. Maybe I have to do 2 night shifts every 10 days. So in a set of 10 days, those 10 variables I have to take between 1 and 2 times a night shift. That's what the among constraints will tell you to do. So it's very useful in these kind of scaling problems or shift scaling problems. Regardless of the definition, we can design a propagation algorithm for this, that uses just domain propagation or MDD propagation, and I just want to give you an illustration of what it can do for you. So if you look at the search space, if you compare a with one MDD, which is basically the domains only, you don't do any refinement, so this is exactly just a domain propagation, or with 16 MDD propagation, how much you can reduce the search space. And this is a log scale. So for some problems, the domain propagation needs 1 million search nodes, whereas you only need 10 search nodes if you were to propagate an MDD of size 16. These instances have up to 50 variables and up to 200 constraints, and they are overlapping. So a width of 16 is not nearly sufficient to represent it exactly, I can tell you that. But it's very, very useful to propagate much more information than just the domain. So you can see that here, and the time is reflecting almost exactly the same thing. So this indicates that at least for this specific problem, MDD propagation can be orders of magnitude more effective than domain propagation. Cool. You can also group these among constraints together. So for example, if I take my among constraints for this nurse scaling problem again, maybe you have the requirement that every 9 consecutive days you have to work at least at most 7 days. This is the very same nurse scaling problem. So for the first 9 days, I have an among. Among these, work at most 7 days. It's just a linear, inequality. It's very simple. But this now holds for every 9 consecutive days in this specific application. And this is a very common pattern that recurs very, very often in these time scaling problems. So you have this overlapping among constraints, if you want. And since they occur in so many problems, and it's a very powerful combinatorial structure, in CP libraries nowadays you have the sequence constraints that groups together these among constraints. Don't worry about the details, it's just showing that you can group them together and do more. What does that give you? Well, you can do again domain propagation versus MDD propagation. So here I have the 3 best domain propagators from the literature, and here I have the MDD propagator with width 2, 32, and 128. So how much would you gain if you would invoke MDD propagation over domain propagation? Here is the time in log scale, and here is the number of instances solved. This is a performance plot. So up to basically below 0.1 second or so, the domain propagators do fairly well. But very quickly, the MDD propagator, for example, this very first one has only a width 2 MDD. It's extremely small. And it takes over very quickly, and it can solve many more instances than the domain propagators can, and the width 128 outperforms everybody else. In other words, with the MDD propagation, you can solve many more instances than you can do with your domain propagation. So this is just an illustration to show you the power of MDDs over the domains. Okay, so you see increasing widths are better, but it's a bit more time consuming to you have a ramp up cost. Yes, that's true. But these are sequence constraints. They are composed of these among constraints. Couldn't we just use among constraints, forget about sequence, that special structure here, and just crank up our width? No, we could not. Because if you take the among constraints and propagate MDDs through here, you see that they're almost all the same power, regardless of the width from 2 to 128. And the real power in this case comes again from the sequence structure. So this shows that, and this is a very, very brief summary of a lot of work that we've done. Standard constraint programming can work well, but with domain propagation you lose out on certain combinatorial structures. Domain propagation can be greatly improved by MDDs, but just having an MDD is not sufficient. You have to exploit sometimes additional structure. Going from amongs, for example, to groups of among constraints gives you orders of magnitude more power. In other words, what we are after, especially for sequencing and scheduling, is, of course, you want to use MDDs, but then we have to find out which constraints to propagate. And we cannot just have an MDD and throw arbitrary things. We just trust that the large width MDD does the work for us. No, we have to do a bit more. We have to be clever in the structures that we represent. Okay? Are there any questions? Yes.
So, in the constraint satisfaction literature, there's people sometimes use higher levels of consistency like patterns.
Yes.
Is there any relationship between these higher levels of consistency and MDD loadings?
Yes. What you could do is you could take so the classical way is to have to take the intersection of two constraints and then project it back on the original domains represented by the original variables. So for example, what you could do here, if you have an MDD for one constraint and an MDD for another constraint, you can take their intersection, and then you can project that intersection back onto the variable domains of the original constraints. And that would be similar to a higher order consistency. And let me think which one that is. It's not immediately path consistency, but it would work. It would be, I think, in some cases better than path consistency if you do it in every pair of constraints, just systematically. It is not true that path consistency can be, at least I don't think it's true, that MDDs can replace path consistency altogether. So you really need to simultaneously evaluate two constraints that are linked together in one MDD. So you can, it's not sufficient to transmit one MDD from one constraint to the next, even if it is exact. There are some other nuances there, and maybe you can take it offline, because you can do some Lagrangian propagation that would actually be very similar to path consistency or similar notions, but maybe you can take it off. So what I showed you here was basically just constraint propagation for feasibility problems. In general, we have optimization problems with an objective, and John's focuses mainly on optimization problems. So we will have objective functions. And the way to encode them in decision diagrams is my very first example. Suppose you have an objective function on top of this set covering problem, maybe like this, very simple weighted sum. What you can do is you can associate with every edge here a cost, representing the cost of the corresponding variable assignment. So if I would assign x1 1, I would incur a cost of 4, so I get a 4 on that arc. I get a 0 on that arc, and I omit the zeros here for clarity. So every arc now has a cost, and the shortest path here gives you the optimal solution if the MDD is exact. If the MDD is relaxed, it gives you a lower bound. That was treated in detail in the previous tutorial. Okay. All right. Now let's go to discrete scheduling. I don't have to explain to you how important that is and how diverse the applications are. I do want to point out that I'm from an OR background as well. So what I typically look at is single machine scheduling problems or multi-machine scheduling problems, as well as routing problems. They can be cast as discrete scheduling problems where every visit is an activity, and I have to sequence all these activities over time. And if I go from one activity to the next, this is represented by a sequence-dependent set of costs. And that's the distance from I to j. So these are all the discrete scheduling problems. And as I'm coming from a constraint-based world, I will use constraint-based scheduling to represent them. I have activities and resources. And most CP systems give you that as an interface, where you can model at that layer or at that level. For example, iLog's CP optimizer does that, but many others do as well. Every activity has a processing time, a release time, and a deadline, or due date. In this case, I use a deadline, and a start time variable. This is the core variable that most solvers use, these constraint-based solvers, in their mechanisms, their solving mechanisms. Oftentimes, processing times can also be variable. Now, I treat them as fixed, but they may be variable. That's fine. Resources in general can be anything in the constraint-based world. I'm just using here the single machine scheduling column, not reactive, and one activity at a time. So I'm really sequencing these activities over time. Okay. What else can we do here? This is quite a generic framework. So we have precedence constraints, sequence-dependent setup times, and a range of objective functions. So you can do basically anything you want, anything you can express in your CP solver, CP mechanism can work, including these standard scheduling constraints. The most useful ones are the make span and the sum of completion times. Those are the most often used. But many other things you can express as well. If you give a model like this to a CP solver, what it tries to do is mainly shorten the intervals for each activity. If each activity has an interval that is tight, then you have no more room, so you have basically fixed your solution. In any case, if you have a linear ordering on the activities, you're also done, but they try to shorten the intervals. Interval is a release and deadline for so the earliest start time and the latest completion time for each task. And one key thing that drives this are precedence constraints among the tasks. After all, a linear order is given by all precedence constraints among the tasks. If you have all the precedence constraints, you have your linear order. So you try to get as many of them as you can, and you have sophisticated techniques for doing that. So for example, from this particular instance, you might deduce that task 1 must always come before task 3. Otherwise, it's not possible to sequence it. And also, you can then deduce that the start time of 3 must be at least 3. Those are the kind of things you can reason about. Now, in this framework, finding all precedence constraints is going to be hard as 0 is no problem. So you have approximations. You usually have bound reasoning, but they can be very, very effective. So you could argue that for constraint programming systems, distributive scheduling is the killer application. I use it all the time for my industrial projects. It's very fast, extremely efficient, and you can add any side constraint, so it's very generic. So I like it very much. It's really among the state of the art. So oftentimes it beats dedicated mechanisms for specific applications, and you just have to solve it and press the button. So I mean, just to model it and press solve, and it can be very, very strong. However, because you only hear about this, what you do not hear is the darker side of CP solvers. This is mainly for make-span problems, typically. If you have a make-span problem, then it's fine. But if you work on an industrial application, most people don't care too much about make-span. They want to minimize the number of late jobs. They want to minimize the sum of the weighted completion times. If you give those objectives, I mean, I'm talking about the industrial setting here, to a CP solver, then it's going to have problems, because it cannot represent very well the objective function by default. The propagation mechanisms are not very strong. Everything is treated separately. I mean, the objective and the constraints are separated. So it's going to have trouble there, maybe. Also, when you have setup times, sequence-dependent setup times, it also degrades typically the performance of the propagation. Basically, there's too many options, and there's not enough power to reason over it in an efficient way. So you can see some issues there. You have a question?
Yeah, I'm not familiar with make-span, that phrase. What is make-span?
The end time of the overall schedule. Okay. So the last activity, when that's done, that's the make-span. So I can now, of course, what I would like to do is try to improve CP rather than complaining that it doesn't work very well. So if I want to use MDDs in the context of CP, I'm not going to focus on make-span problems necessarily, because they are really state of the art there. I don't have to improve them. We do a little bit, so it's fine, but I don't care, because they are great. What I really care about is, can I improve CP where it is currently not working very well in these contexts? So that's optimization and setup times, and that's exactly what I'm going to focus on. So our goal is now, can we represent and reason on such problems in the context of MDDs? So what are the things we have to think about? First of all, how do we represent this disjunctive scheduling problem in an MDD? You may have some ideas here already. If you know how to represent it ideally in an exact exponential size manner, which is what we don't want, how do we construct this in an efficient way? And if we have it, what can we do with that? How can we mix it with the other techniques that we have? Because I don't want to throw away the power of CP. I want to keep all the domain propagation. I want to keep all the scheduling software that they have. They are fantastic. I just want to add my technology. So it has to really be embedded, right? So you have many choices for the representation. You could, for example, pick the start times, the start time of activity 1, the start time of activity 2, and so forth. But if I don't know the ordering, it is not a, I think, very useful recursive structure to first have activity 1's start time, then activity 2's start time, especially when activity 2 becomes way for activity 1. So rather, I would like to represent it as the linear order in which this disjunctive scheduling problem will be solved. So in the end, a solution to my problem will be a sequencing of the activities. So this is the first one, the second one, the third one, and the nth activity that I'm going to execute. This may be job 5, job 3, job 10, job 1. That linear order is my solution. Given their release times and deadlines, I can now compute their start times. It follows automatically from my linear order. Sometimes you have a choice. For example, if your objective is minimize the sum of the weighted completion times, you just take the start times to be the minimum. But sometimes there's a choice when you have, for example, tardiness or other more complex functions. But that's fine, you have a range in which you can search further. So the sequencing problem is solved when I have the linear order among the activities. So that's what I will represent. In other words, if I have 3 activities, 1, 2, and 3, each having a release, deadline, and a processing time, I will represent an MDD saying the first layer represents the first activity on my machine, then the second, and then the third activity. If you look at this, you see that the deadline of activity 1 is 3, and activity 2 and 3 can start at the earliest at 3 and 4. So there's no way I can schedule 2 and 3 before 1. In other words, the first activity on my machine must be 1. So the label that I give to the first edge is 1. Okay? And then I can take either 2 and then 3, or 3 and then 2. So here I have both solutions to this disjunctive scheduling. Do you agree? Yes, hopefully. It's not so hard. So if I take any path, then I get a solution, at least a sequence. And you can choose now what you like as starting times. Your starting time for 1 is between 0 and 1. These are the bounds for 2 and 3. And depending on your objective, you can search further on your start times or just take a minimum if you are happy with the minimum. For example, for makespan, the minimum would work and so forth. Okay. So this is what I want to achieve. This is the exact representation for this problem. And I don't have the objective given to it, but this is all solutions. Unfortunately, of course, all solutions are represented here. So, of course, it must be NP hard to construct this thing because this scheduling is NP hard. But that's fine. I'm going to work with relaxations and I'm going to find ways to make it tractable. However, sometimes there is, you can show that it's actually very nicely bounded. And the size of the exact MDD is actually polynomial time or polynomial size. And there is one nice example of Balázs. He presented the following case. Suppose we have a traveling salesman problem. And we have our indices, we have our locations index of 1 to n. If index j minus index I is at least k, then I must have the preference icon before j. Where does this come from? This came from the following application. They solved actually a single machine scheduling problem for this industrial application, and they found a solution, which was a TSP tour. And now they wanted to improve it, but they didn't want to disrupt too much the overall schedule. So you were allowed to find a solution as long as the largest schedule was still intact. So if 2 activities, j and I, are far away, if there are k steps away in your solution, then you cannot move them one beyond the other. So I must go before j if I comes way before j in the tour. So if there are at least k steps in between. And that helps you construct a tour that's different, but still keeps intact the overall idea. So it is, you can find another solution within the context of an existing solution that's given to you, for example, in an industrial context. For this particular instance of the DSP, you can prove that the MDD is exact as a polynomial bound 2 to the k times n, and that means you can optimize any objective over this also in polynomial time. Now, Balázs also introduced this problem with a polynomial time algorithm. It was a dedicated method. This result follows immediately from our scheme, so it is a nice side effect, I would say. So in some cases you are lucky and you can actually get polynomial bounded MDDs, but in general it's going to be exponential. Okay. So the two tasks that remain are, I want to construct the MDD, and given the MDD I want to filter them, I want to propagate. So let's start with the propagation. I'm going to assume you give me your MDD, or the relaxed MDD, and now I'm going to filter it, I'm going to propagate it. And I want to remove all those arcs that are provably not in a solution. What are my constraints? Well, the permutation structure gives me an all different. Each job must appear exactly once on each path. I have the intervals for earliest start and latest end time, and I have precedence constraints. There may be more constraints, but so far these are the only ones I have given to you. Okay. You also have the objective, but I would like to postpone that for later. These are the most important combinatorial constraints from sequencing. In Joe's tutorial, he said we can do a top-down compilation of the MDDs. We will take a similar approach. And we also take a similar approach to John's tutorial in that we have state information. This of course is very similar to dynamic programming. You can see the similarities already maybe in the previous slides. For every combinatorial structure, for the all different, for the earliest start time, for the precedence constraints, we have to reason over them at the state level. So we have to somehow represent that information. And we will make sure that the reasoning we do relies only on the state information at each node, so it must have the Markovian property, and then we are going to do it. So let me show you how that works. I'm going to do this by illustration, but I think that works the best. Suppose here we have a snapshot of a MDD. The first 4 layers of the MDD. This is given to us, it's a relaxed MDD. I have here the set 1, 2. That means there are 2 arcs from R to this node. I can either take the activity 1 or activity 2 as the first activity on my machine. Okay, so this is a set of all possible values, and so these are actually 2 parallel arcs, right? So the state information I'm going to need is the following. I want to know which are the jobs that have been processed so far, and what is the earliest starting time they might complete. So that's exactly what I have in these states. The labels that occur on all the paths is going to be A of I for state I. The labels that occur on some paths into a state, for example U, is Si. I'll show you more details later. I'm also going to maintain the earliest and latest completion time, or starting time and completion time for each state. These are concepts that you have seen, that you yourself, if you work on scheduling, you use all the time, because it's just your temporal network basically. And that's also what we will use. So let's focus on this node here, U. The first state I will compute there is the state of all the labels that occur on all paths into this state. So if you look, any path uses 3. Not any path uses 1. For example, what I could do, I could take 2, 2, and 3. So that's one path that does not use 1. I can also take 1, 1, 3, so also 2 doesn't need to be on all paths. Okay. So the label that occurs on all paths from the root to U is 3, and only 3. So once I am in this state, I know that 3 has been scheduled, for sure. It's a disjunctive scheduling, probably all different, constraint must hold, so I can eliminate 3 from this domain right there. Okay. And these are, before, these are 5 parallel arcs, and now I kill 1 arc. Okay. Is it clear? Okay, good. Now you can do a little bit more, because I also can collect all the states, or all the labels that occur on some path. For example, 1, 2, or 3 all occur on some path from R to U. Right. And why is this useful? Well, I have so far only used 3 slots in my schedule. I have 3 slots, and the number of labels that can be used is 1, 2, or 3. And so I have 3 slots, 3 labels, so in some order they have to be allocated. So I know 1, 2, and 3 will all get used somehow in the first 3 slots. And this is called a whole set from the old diff literature, if you want. And so if the cardinality of your set of sum is the same as the cardinality of activities you have so far processed, or the layer where you're at right now, then if that's equal, then you can remove those values from those outgoing arcs. In this case, 1 and 2 can be removed, because they must be scattered somehow before in a solution. Okay. What I actually did now is I basically lifted the all different filtering from domains to multi-value decision diagrams, MDDs. If you are familiar with the all different propagator, we do exactly that. The next thing I would like to filter are the earliest completion times, or the start times. So that E of U represents the earliest completion time of this at U among all paths. This is basically a simple dynamic programming recursion. So if I give you an instance, you don't have to go over the details. You just associate with all the states. What is the minimum cost to go from R to this state? Well, I can take 1. Because it starts at 0, it takes 2 times. I have 2, then I have, in this case again 2, it's 4, and then I take 3, which makes 7. This is the shortest path from R to U relative to the processing times. Very simple. I know that 4 can only finish before 6 as a deadline, so if this earliest start time of 7 is higher than I can start my task 6 in this case, I can remove it, so I can remove 4. It's a very simple rule, and it works very well, of course. Okay? This is not too deep. And of course I can do the same with the latest completion times going from the bottom up. I hope you see that. Now the interesting thing comes with the precedence relations. As I told you before, these are the main drivers for standard domain propagation, and together with the interval reductions. So I have a precedence constraint I comes before j, and if I look at an arc with label j, for example this arc 5 here, it is infeasible if I comes before j and I is not on some path into that node. If I can never ever achieve that constraint, satisfy that constraint. So I can now borrow from the all different constraint the set of some states, and suppose that 4 must come before 5. This is a given precedence constraint. And I expect by the sum state of U that there's not some path on which 4 occurs. So that means I can never satisfy this precedence constraint, so 5 cannot appear there. If I had scheduled 5 here, I cannot satisfy the constraint, so I can propagate that constraint and remove that arc as well. So my MDD becomes very small. Actually I have here an empty layer, so basically I'm done. I show it's infeasible. But suppose there's another part of the MDD, or it's part of a larger search process, then you can still continue. But this is how you do the precedence constraints. And you can reuse the states from the all different for this particular case. Okay? Are there any questions for this? Now the nice thing is that if you give me the exact MDD, I can give you all the activity precedences in polynomial time in the size of the MDD. But the MDD can be of exponential size, obviously. And this is not a big surprise, because if you have the MDD, I have the entire solution is already solved. That in itself is not so interesting, that you can reduce all activity precedences. What may be interesting is that you can do this in polynomial time. It's particularly interesting because you are not giving me the exact MDD, but you're going to give me the relaxed MDD, and I can apply the same mechanism to reduce all precedences for a relaxed MDD as far as I can. For this particular proof, which I show you in a constructive way, because you the algorithm to get the precedences, I use again the all states, all label states for the all different constraints. So for every node U, I have the labels that occur on all paths from the top, this is 1, and all paths from the bottom. So I separate them in 2 parts. What I will use is that the precedence constraint holds if this condition is true. I comes before j if and only if j does not appear in all states from the top, or in all paths from the top, or I does not appear in all paths from the bottom. And this must hold for all nodes u and m. Okay. So how does that work? So this is, I think, a very nice way of getting it. So if you are interested in getting the precedence constraints for a scheduling problem, you might find this an interesting way to do that. What I will do, I'll give you a polynomial time algorithm to get you all the precedence constraints from a given m. I will build a graph that represents the precedences that cannot hold. And then I'll take the complement of that, and that gives me all the precedences that must hold. So I will actually use this fact, and I will expose via all the nodes which of those constraints do not satisfy this condition. And that populates my graph of precedence constraints that cannot hold. But this is how it works. I give you an example right here. Suppose this is our exact MDD. And my task is give me all precedence constraints. Alright. I'll build a precedence graph. In this case it's the complement. These are going to be all the arcs that represent precedence constraints that cannot hold. And this is the exact MDD. It's a given. So here are the two states that I need. So let's consider the first root node. Well, all the labels that go from the roots to all to this R is of course empty, and from the bottom to this state is all the labels, right? So that's fine. That's not interesting. But let's look at this one: 3 and 1, 2, 4. All the paths state value 3, and all the paths state 1, 2, 4 from the bottom. What do we know? Well, we know now that since this is the exact MDD and 3 comes before 1, 2, and 4, the opposite cannot hold, because this is the exact MDD. So those precedence constraints cannot hold. For example, it cannot be that 1 must come before 3, or 2 comes before 3, or 4 comes before 3. I can just inspect that. So I can just do that for this node, and I can populate this graph. I can go to the next state, and I can induce also that 1 cannot come before 4. So 4 before 1 is not true, and 2 before 1 is not true. Because I have here a witness that shows me the opposite. And I go over all of these states, and I update the graph of precedence constraints that cannot hold, because I expose a solution that actually shows that they are not holding. And every time I go through a state, I update my graph until I'm done. So here are all the precedence constraints for this exact MDD that cannot hold. That means that the opposite, the complement, are all the precedence constraints that must hold. Okay? And here you have 3 comes before 1 and so forth. These are the precedence constraints that must hold. What's the time complexity of this? Well, of course you have to go over each of these states. You have to do a comparison here, which is basically order n times order n, quadratic comparison. So the very rough estimate of the time complexity is n squared times the size of the MDD. But it's polynomial. Okay? Now I use the fact here that's the exact, and we have the all states. But in general, I don't have an exact MDD. I have a relaxed MDD. How can I make this work? I'm not going to use anymore the all states. I'm going to use the sum states and do the exact same thing. Why does that work? Because if I use the sum states, I will predict that a precedence constraint may not hold. So I will make this graph larger and the complement smaller. And so I get a subset of precedence constraints. Okay. And that still works. And the beauty is that we have a discrete structure from getting these precedence constraints that's quite different from all the edge finding and other rules that have been used before. So we can find edges here, or a precedence constraint that cannot be detected by other methods, which is a very nice complementary power for existing methods. There also exist applications, cases that we can detect certain propagation that others cannot. I don't know if we have to go into the details here, but here's one illustration for a problem in which edge finding and not first not last may deduce precedences but don't update the time bounds. And here's an example that shows you that we actually do also have the precedences and we have the time bounds at the same time. So we can outperform existing methods in theory. We don't dominate them always. I mean, if you, of course, if you have an exact MDD, we can outperform everything, but that's going to be hard. But there's a trade-off. With a small width MDD, you may get enough power to actually be better. So what can we do? Well, since we have now precedence constraints, we can give them back to CP, and CP may use them for further inference. And also we can use the CP precedences to filter the MDD. So there's a nice synergy there. So far we have our MDDs given, we have propagation, but how do we start all this? Well, in general, we start with a very simple MDD. Like this. And I think, by the way, this is a nice, maybe a break point for a sanitary break. Before we go further, who would like to have a sanitary break? Nobody does. You would like to have a sanitary break? I don't want to.
We don't have to.
We don't have to. Are you sure?
Awesome.
Okay, apparently there's not enough peer pressure to stop now, so I'm going to discontinue. Feel free to leave and so let's see how this all works. So how do I get this MDD? This is going to be one slide showing you how we do that. So in the beginning we don't know how we can construct it, so we just have one edge, or basically 3 parallel edges for every layer. All possible values could be taken in any position. Suppose I have this one precedence constraint. 3 must go before 1. It's an side constraint. Okay, what can I deduce? I can do some propagation now. What is the propagation? 3 must come before 1, so I can filter 1 from this spot. If I start with 1, I violate the constraint. Agreed? So that's one propagation I can do. If you have the bottom up as well, you can also remove 3. But I'm really focusing on the top-down computation. Alright, still we have no solution. So what we can do now is what we call splitting or refining the MDD. So these 2 paths, 2 and 3, into this state are quite different, of course, because they represent different solutions. What would happen if I split the MDD, like so? I may be able to represent better my solutions. So if I split the MDD, I take these 2 arcs, 2 and 3, I split them, and I copy the outgoing arcs accordingly. Okay? What can I do now? Well, I can do propagation of all different. I can still do the precedence constraint propagation, but for example, the all different tells me that 2 cannot occur here anymore, and 3 cannot occur there anymore. So now I propagate the all different. I also can propagate, I think, the precedence constraint right here. 3 has not yet occurred, so I cannot have 1. That's very nice. And then I can maybe split this, still not the exact MDD, so let's split this further. And I have options. I have 3, 1 and 2. Suppose I group together 3 and 2 as they are right now, and I just split off the 1. So I just pull out the 1 and I do that, then I have further propagation of the all diff, because I have 2 and 3 and 3 and 2, so this is a whole set. So 2 and 3 can be removed there, and in this case I can remove 1 and 3 via the all diff. Okay. And this gives me the exact MDD by splitting and refining the MDD as I go. So in a larger scheme of things, what we try to do is manipulate this MDD as we go during search of the constraint programming search. So in the outer search for CP, this thing is there, it's propagated by all the constraints that we tell it to be propagated on. All diff, early start times, precedence constraint, time windows, or anything else you would like. And we maintain this structure here. If we have a maximum width of 2, we're going to be perfectly fine. But maybe we have a limit of 2. But then by propagation, we may actually remove arcs and states, and then we refine further as much as we can. And that helps us. Okay. The refinement is very important here. If you were also here with John's tutorial, he said merging So to define what you do with the top-down combination method in this case for getting the bounds, you would have to define a dynamic programming recursion, which we somehow did, but very implicitly here, and a merging rule. We do the opposite. Instead of merging, we do splitting. So as important merging was in the previous tutorial, is refining here. Typically what you want to do to obtain the exact MDD is to identify equivalence classes. They would correspond to knowing a priori, when you split, that the two subtrees are isomorphic. Or when they are isomorphic, you can actually merge them. But that's an NP hard task in general, certainly for this scattering problem. What we use is state information for all diff and for earlier start and latest completion. In other words, it can be driven by the number of jobs already taken, so as to preserve this all different structure, so you can prove many of those, or it's driven by the objective. In other words, earlier start time, for example. So we implemented this in the state-of-the-art constraint-based scheduler, CPU optimizer. It's a very strong tool. It's very, very clever. It actually uses LP relaxations as well, so it does do some optimization reasoning. It was not as bad as it used to be for solving more complex objective functions, but still, it's not always doing a great job. And so what we are going to focus on is what does CPO, the CPU optimizer, do by itself? Just do the main standard constraint-based scheduling. What do we just by ourselves do? And what happens if we combine them? As I said before, we can do many different problems, so we chose some of them. We look at sequence-dependent setup times, because we know that CP is weak there. I mean, I can tell you up front, CPO is fantastic on make-span problems that are pure make-span problems. Okay, so without even running it, since CPO solves all these instances within a split second, I'm not going to beat it, right? So that's fine. So let's take it as a given. It won't hurt much to add MDDs, but you cannot gain much because it's already so strong. We want to focus on sequence-dependent setup times, tight time windows, presence constraints, and other objectives than just make-span, but also make-span. So let's look at what we see. First of all, let's look at the importance of this sequence-dependent setup time. I told you before that influences the power of CP. And we have random instances where we increase the length of the setup times. So this is by increasing length. Okay. So if you have very small setup times, almost zero, then the CPO backtracks over the MDD backtracks is about, let's say, 0.01. That means that CPO uses about 100 times fewer backtracks than a pure MDD scheduler. So the pure MDD scheduler says we turn off all features of CP and we only use our MDDs and nothing else. That beautiful black box CPO, we don't use any of that. If we do that, then they are about 100 times faster. If you increase the length of this, and this is for very simple minimized make-span problem with nothing else, it's extremely simple, just to test the importance of the setup times. If you have a little bit more important setup times, we are break even, and if you have, if they become more and more important, we can get up to 100 times faster than CPO. So you do see that the presence of setup times does influence by itself already the performance of MDDs and CPO. But even if there are no setup times, you can still outperform CPO quite a bit. So let's look at a problem in which setup times are very important. The most important class is the traveling salesman problem, because you have no processing time. You have basically, or in this case, you have time windows. So let's assume you have time windows as well. It's a scheduling problem with mainly sequence-dependent setup times. It's really bad for CP because you have to minimize the sum of the setup times for the TSP, right? This is the classic benchmark, and you see here that in terms of time, this is a log scale. Of course, but the pure MDD greatly outperforms pure CP. This is our orders of magnitudes. You can solve many more problems optimally than CP would. This shows you that MDDs just by themselves can outperform CP, but I want to stress that CP is not the preferred method for TSPs, right? So if you are an advocate of the devil, you can say you're going to compare with garbage. Of course, you're going to do better. I'm not saying that CPO is garbage, but for TSP it's not really good. If the time windows are tight and are suitable, then CPO can be very good actually, but this is not always the case. But if you just look at pure MDDs, it's already much better. Right? But to put things in perspective, this is the first iteration. This is a very well-known benchmark instance. Some of these instances were closed just a couple of years ago with a dedicated method, which is quite complex. I can tell you that our method now is competitive with the best methods out there. So we can close all these 8 benchmarks from these, all the instances from this benchmark in a reasonable time, and sometimes we're faster than the best known algorithms that are out there. That to put it in perspective, right? Another example would be total tardiness, where you look at how at the tardiness of each task, so it's either on time or using tardiness factor, and you want to minimize the weighted tardiness, which are extremely difficult to solve optimally. If you are used to solving planning problems with thousands of activities and tasks, you're not going to be very impressed by a 15 activity instance. I can tell you we can solve much larger ones, perhaps not optimally, but we can solve instances with thousands of activities without problems in terms of scalability, but I just cannot guarantee optimality. If I want to compare, then I need to have small enough instances to show you something, because we're doing an academic comparison here. So in terms of scalability, I can tell you it does scale, but not necessarily optimal. So for total tardiness, here are the results. Again, performance plots, number of instances solved optimally for the standard CPO engine, and then MDDs of increasing width. And MDD of width 128 is not nearly enough to find all the solutions exactly. So, but it solves it much faster. So you see the enormous impact that this MDDs can have for CPO for these problems. These are for unweighted. If you have weighted tardiness, it's a little bit different, but soon MDDs of standard size are going to be taking over CPO. The last one is a traveling salesman problem with precedence constraints, which is a pure TSP with precedence constraints. There's no time windows, there's very little structure here. So we use all these extreme cases to have a wide range of applications. They are very hard. Here you see instances that have only 43 locations and that were open. And that we closed for the first time. This was a number of years ago, so I think we closed a few more now, but Andre has the results. Many people looked at these problems before, so all dedicated methods could not solve these instances, and this out-of-the-box MDD plus CP approach solves them optimally. Not all of them, but it does a good job. For this we used width 2048. We really wanted to crank this problem, and so what we did, we filled up our memory as much as we could in a reasonable amount of time. So with 2048 is fine. So you can really fill up your memory and reason over it as you like. These are nice results as well. But, I mean, there's no but. I mean, this is fine, you close all this, that's okay, but there's still, it's not so robust. What we found is, for some problems CP did well, other methods do well. Why don't we blast all these things away? What is still wrong here? What do we not capture? There's obviously something we cannot solve all these instances, and also for the TSP with time windows. There are some instances that we also have trouble with. We were not, 3 years ago, able to compete with the state of the art. What are we missing? Well, what we are missing is that in our MDDs, as it was mentioned also in the previous tutorial, we have these relaxations in which tasks can be repeated. So the shortest path may be 1, 2, 2. And that repetition of activities is a given because we are a relaxation. That's exactly what we relax. We don't relax the early start time of the shortest path, it's exact. We don't relax precedence constraints necessarily. We mainly relax repetition of tasks. And that's very bad, and it can really hurt us. The nice thing is there is a mechanism from operational research, from mathematical programming, called Lagrangian relaxations. And it fits very well this framework of MDDs. And I'm not sure if everybody is familiar with that, but I'm going to give you a high-level intuition for that. So if you would write this down in a sort of linear way, what we are doing, and you would write down the constraint that each task must occur exactly once, this is what it would look like. This is an expression saying it is true if the ith activity is j. So layer I takes j, basically. This is a Boolean, okay? The indicator function. And the sum over all activities, so for every activity j, the sum of all the layers must be 1. So you have to schedule activity j exactly once over all the layers. This is the, you can also encode this with a Boolean xij equals 1, right? That's it. That constraint we violate. And we don't do anything with it. But it's right there. What you normally would do in a Lagrangian optimization is you would take constraints and you would penalize them in the objective. So you take the difference between the left-hand side and the right-hand side. There's difference right there. And you give it a Lagrangian multiplier, penalty. It's a fixed constant. And if the constraint is satisfied, this whole term falls away into 0. If it is not, it incurs some kind of penalty. Now, Lagrangians give you a bound on the objective, a lower bound in our case, regardless of the lambda, the penalty that you choose. And the challenge would be, find the lambdas that give you the tightest bound. That's, you typically use a separated method for that, but that's fine. You don't need to do that optimally. Any set of penalties will work and gives you a bound. Maybe worse, maybe better than your original. And what is nice about our case is that we already violate the constraints. The only thing we don't do yet is assign penalties. So it's a very little effort to actually start adding penalties to it. And what you can do, you can split out this sum, and you can recognize that the lambdas fall into a constant part that just can be discarded for the optimization, and a lambda times the assignment that in the ith layer you take j. The assignment that in an ith layer you take j is exactly an arc in this layer. For example, it would be pi2 equals 2. And with that I have a lambda. In other words, I used to have a cost associated with this arc, and the shortest path takes that cost. That's in Z. This is my shortest path. It sums the shortest path where the arcs have costs, right? And now I update that with every decision that every arc here gets an additional lambda. So the original cost just has one more additive factor of lambda. That's the only thing I need to do. So I just have a shortest path with updated weights. So the whole machine remains exactly intact. The only thing I need to do is add lambdas, maybe do a couple of iterations, maybe 10 or 20, to do my subgradient, to find the best ones or good enough ones, and improve my bounds. And it's almost for free. How much does that smoothen or outperform our previous method? Well, let's see. These are again the TSV with time windows, because we really want it to be the state of the art there. This is without Lagrange multipliers, and this is with Lagrange multipliers, the optimality gap at the root node. So if I add the Lagrangian penalties, I can dramatically push down the gap from, say, 25% to below 5%, which is a huge decrease in the optimality gap. So my bound at the root node is much reduced, and this is the number of instances that you can solve over time. So the upper part here is the Lagrangian bound, and the Lagrangian propagation, and this one is the standard one. So we can solve many more instances with this approach. And this allows us, with a few other tweaks, to now be competitive with the state-of-the-art for the T's and the time. Okay.
Sorry, I got a bit lost in the end. How are you actually computing the Lagrangians? So, do you have to take into account that a certain value was selected before or
yes,
not?
Yes.
But how are you saving this information in the end?
You are a bit familiar with Lagrangians?
Yeah.
Okay, great. Then this will work. So here's an instance with 3 tasks, very similar to the previous example, and you see them all here. These are costs that are originally the costs I associate with that. They are the processing times, basically.
The blue.
What's that?
You mean the blue arcs are the costs?
Oh, no, sorry. Let me just go a little bit more in detail. So we have 3 tasks, blue, orange, and green. They are blue, orange, and green.
Oh, I see.
And they appear everywhere. And they have a release date and a processing time. So for example, if this is for a makespan problem, and I accumulate the time throughout the layers. So for example, if I execute this blue task, I can start at 2, it takes 2, so if I take that, I finish at 4. and then that accumulates my make span so far. And then I add, for example, this green one, which can start after 1, which is fine, and adds to that 3, so I have a 3. So the sum of these arc weights correspond to my make span. So what's the shortest path here? The shortest path is this. It has weight 8, 4 to 8. Okay, and this is this is a lower bound. That's fine. I didn't tell you what the optimal is. I think it's 11 or 12. And here is the solution for this path. And the issue is that we have repeated here this task twice. So to your question, how do I update that? Well, I use if you're familiar with the held carp bound, but I can count how often is a task repeated and how often is a task or it is not used. So if a task is here, if a task is repeated, I'm going to increase its weight. That means that I'm going to try to divert the solution from taking that task too often. If a task is unused, I'm going to decrease its weight because it's going to be more appealing. So the lambdas, so the arc cost is going to be in the Lagrangian updates. I'm going to take the current cost plus a step size multiplied by how often it is repeated or unused. So that's the current occurrence. It's 1 minus the current occurrence. Okay. So in this case, for example, what I could do, I could take a step size of 1 and I update my costs by a factor of 1 when this happens. So that means that this blue task will get increased by 1, and the which one is not used? Red. So red will be decreased by 1. And since they balance out, I don't have to worry about the constant term in my Lagrangian, by the way. If I do that, these are the updated costs. So all the blues get 1 more, all the reds get 1 less. And these are valid penalties, and I can recompute the shortest path, and now this is my shortest path. 4, 3, and 3, which gives me 10. So I go from 8 to 10. This is, I think, the optimal as well. And there's another one, I think, which has the same 4, 3, 3, which also has 10, which is actually a proper solution. So 10 is the optimal solution in this case. So with one iteration, the bound is the same as my objective value. The bound is not necessarily a solution. The shortest path is not necessarily a solution, but the bound itself is the optimal value. Is that clear?
Okay.
And also I can do filtering. So for example, if an arc does not correspond to an improving solution, then I can remove it if it doesn't belong to such a solution. So for example, suppose I know that the value of 10 is known, and I look at this arc, then the shortest path through this arc would take 4, 4, and 3, and would be 11, so I can remove that arc. This can be also done in a straightforward way. Okay. So if I have this could be done before already, but now with the Lagrangian penalties, that filtering is still valid. I can get more propagation there as well. And that gives you these nice results. But again, this is very generic. We don't use it only for sequencing probes, we also use it for many other applications. You can basically dualize any constraint that is violated by the MDD in the objective. So it's very generic again. So as last topic, I wanted to show you that you can also have state-dependent costs. I'm going to take this one simple application, but you are familiar, many of you, with state spaces and MDPs and that kind of stuff, so you won't be too surprised that you can do it. I just want to show you how we do it in this context and what's the benefit. So I probably in this audience don't have to defend or motivate too much that time dependency is very important. Distance matrix is typically never taken for granted, especially when you do routing. It depends on the time of the day, traffic, and so forth. So time-dependent sequencing means in this case, the sequence-dependent setup time depends on when you schedule the activity. It's very hard to do it optimally, and the best methods are dedicated methods, and it's not therefore not too generic, and that's not always easy to work So what can we do? So the only thing that we have to change here is the following. If you have time-dependent setup times, that means that these sequence-dependent setup times, they're going to be state-dependent. Now there are different variations to this. There is the proper time-dependent traveling salesman problem that takes into account the exact minute or hour that you leave a city or leave a location. And you also have position-dependent setup times. And because we were just starting this work, we took the easy route and we take the position-dependent setup times. We are working on extending this to the time-dependent setup times, but this is the position-dependent. And that actually still makes sense in practice. For example, it is maybe more costly to perform certain operations if these are proper setup times that will cost you something. It may be more costly to do something in certain positions than in other positions. So for industrial scheduling problems, machine scheduling problems, this does make sense, and these do find applications by themselves. So we have a setup time that is dependent on the position t in which I is scheduled. A constraint programming model would be like this. So you want to minimize, for a traffic salesman problem at least, the sum of the setup times. And they are now, the setup times I go from position I to position I plus 1. And the setup time depends on location I. So I sum all the positions, for all the positions I sum the setup times, and I have to link them somehow with the precedence constraints. They're going to be fine. This will work. The problem is CP models don't really work well if you have this again, the summation and other constraints separated, so this doesn't work too great in practice. But we can just apply our MDDs here, and the only thing we have to do is change our earliest start and latest end time. That's the only thing we have to do. And that's really easy, because at a certain state in our MDD, we already have the position I available, so that we really have zero work to this update. This is a straightforward extension of what I showed you before. The only thing we do when you do the updates, you take into account the layer that gives you your T, and then you're done. It's very simple. This is a model, and it's, we'll skip over this one. The problem is that it will not work too well. The bounds are not going to be too strong. So what I wanted to show you is how we try to improve the bound. And this is another idea from method programming. And this also shows you another feature of these MDDs. It can incorporate, for example, Lagrangian relaxations, but we can also incorporate linear programming relaxations. So MDDs are great for that purpose. You can just use anything you want that's out there to improve your method. In our case, what we'll do is we use something called additive bounding. If you have a number of relaxations to your problem, each of which gives you a bound and a set of residual costs, then you can basically feed the next relaxation with the residual costs instead of the original costs, which gives you another bound, and so forth. And you can sum them all up, given certain properties on the residual costs, and this together is a valid bound. That means that if you have, for example, for the VSP, you have maybe a spanning tree relaxation and an assignment problem relaxation. You can compute one relaxation, get residual costs, and feed it in the other one. So you don't have just one shot, you can move information from one to the next. And since we also have a relaxation, we can play this role here. We can have a first relaxation being the linear program, and the second one being the decision diagram. And that's what we'll do. If we don't have to go over the details, but from a linear program we get something like reduced costs, which gives you the marginal impact of using a variable, and that's what we'll use in our computations. So let's see how that works. You can build a MIP model and a linear program model for this particular problem, the time-dependent traveling salesman problem with side constraints. It's very straightforward, very similar to an MDD encoding actually, and you get from that reduced costs. So what we'll do, we'll take those reduced costs, and what the additive bounding framework tells us is, if you take any solution in your MDD and you evaluate that with respect to the reduced costs plus the LP bound, that together is a valid bound. And that's what we'll use. So we will augment our MDD with the reduced cost factor. So every edge has now two costs, the original one and the reduced costs. We have extra state information, remembering the original objective, and also our additive bound objective. And we have filtering separately now for this stronger bound. And hopefully that gives us better results. Let me just get to the results here. I want to point out that the MIP model is not the dedicated method that works best for this particular time-dependent DSP. That uses a branch cut and price algorithm, and it's not straightforward to get out of that, for example, reduced cost, because it's a whole framework. What I do want to point out is that the LP relaxation itself, for only 90 vertices, takes already hours to compute. So the MIP model, the main problem here is that it just cannot solve the LP relaxation. And John also pointed out that particular problem. There are scalabilities with MIP as a generic technology, and mainly this is about model size. If you have a big enough computer, you can run it and it will run very well, you get very good bounds, but if the problem gets too big, and it quickly can become too big, then you're going to be in trouble. We did our best to balance the number of valid inequalities that we had to the MIP to make it stronger, but you know, we basically ran out of memory and time. And that's hurt us. So that's why we cannot scale up too much with this particular linear problem. So what does it give us? Well, the MIP by itself solves out of, in the end, 27 instances for which it could find a LP solution. It's, this is the MIP. So let me just say, these are two parts of the graph: the time versus number of instances solved, and then the performance plot. And then once you run out of time, what's your gap? Is your gap 0% or up to 25%? Or up to 50, or up to 100% of optimality. So this, for example, MIP solves about 5 instances optimally, and then 5 instances have a 0 optimality gap at that time. And at that time, let's say 10 instances have up to 25% optimality gap. And you have to go all the way to 70, well, let's say 60 or so, 50 something, to have that's the optimality gap for MIP. So all instances are within 50% optimality. If you just use our MDDs without the additive bounding and LP filtering, you can solve more instances and the gaps are better. And if you add additive bounding to it, you can get way more instances solved, and also your gap is much better. So this shows you, and also for the sequential ordering problem, it's time dependent, you can do something similar, you can solve more instances. Adding together the LP bound and the MDD bound can both improve the MDD and the LP bound separately. So it's not that you just take the max of both, you really can have a synergy there, and you can solve more instances and get better bounds, which is nice. Again, the draw, the bottleneck here is LP solving time. It's just not scaled too well, which is sad, because LP is the workhorse of MIP and used to be not limiting. Normally it should not be limiting. Okay. I think I'll conclude here. The main thing I wanted to point out, that's why I started out with the constraint programming framework. What I showed you is mainly for sequencing and scheduling, but everything we did is embedded in constraint programming. If you have site constraints, even those that cannot be expressed with MDDs or are not handled by MDDs, you can still add them, and the CP solver will take care of them. So it's very rich as an environment, as a system. It outperforms existing methods for distributed scheduling problems, for a wide range of problem classes, so that's very cool. And you can embed different math programming relaxations like Lagrangians or LPs as you like. So I think this is a great addition to constraint-based systems, or even perhaps planning systems. That's the hope, of course. And maybe you can borrow some of this in your own tools. Maybe I can learn from you what you use and make this even better, so that would be nice. So are there any questions?
Yes, I was wondering how much of this machinery can be either reused or adapted to planning problems. So, over, let's say, a bounded horizon, you wouldn't look at the other ones. But, so you don't have all different constraints, that's the big thing. What you may have, though, is a linear constraint where variables are the number of times that each action must be executed. So actions must be, well, in general, executed multiple times. So you can build some of these constraints, saying, you know, well, linear constraints where all the variables are number of times the actions are executed. You also don't have as straightforward, I think. I mean, you wouldn't have as straightforward precedence constraint like, you know, this task is before that other one, because, well, for one thing, they could be executed multiple times, and it's kind of more complicated to see. So I don't know. What do you think? There's any chance that for, you know, you could adapt?
If I didn't think that, I would be here, I think. So it should be possible, I think.
So one thing that
it's not straightforward indeed. And for general planning problems, I still think it's possible. But I think we have to sit down and start. What I would recommend doing is start from a specific application, if possible, and work from there and try to make it more generic. In terms of actions being repeatable, if you have no upper bound on them, it's going to be very challenging, because what we want to do here is get bounds, and that will give you basically a very, very bad bound. So that's very problematic. So if there, on the other hand, are heuristic, if you know somehow how often an action can be taken, maybe that gives you better ways of doing it.
I mean, like one thing to do, so we sometimes solve relaxed planning problems because we use the solution as heuristics in a state-based search to solve the real problem. And this, I mean, some relaxations don't have these, well, you don't repeat actions, which is, I guess,
right. So if you carve out a streamlined version of your planning problem and you say, suppose I have so many times I can use this action or that action and so forth, within that space perhaps you can then bound and find good solutions quickly. But it should be really a sub-problem then of the larger problem. And I think this is also what you just mentioned. Remarks? Okay, thank you for your attention.